So I do thank the organizer for the opportunity to present this ongoing work. And so today I'm going to talk about something that I hope we can do in the future. And so this work is in collaboration with, oh, you are laughing? Okay. Paul and Yasin and Cloudy, the Anthropic AI. So a lot of things that got some input from the Cloudy and I also cross-check it, but I did my best. But there's some experimental details I like to dig into. So if Wei, you're in the back, if I say something terribly wrong, please just shout out and then correct me, okay? And then this talk is a little bit switch of the gear from energy correlator to a more conventional jet observable type of consideration. So this is the email I got from the organizers. So I was asked to talk about anything. So this you have to suffer from this. And but I'll try to be very non-technical because there's experimentalists and theorists, and and I'll try to keep the time so that people can have lunch. And so as I'm going to sort of estimate in the end of the talk, I think the optimistic estimate of the realization of this phenomenology, I would say probably 10 years later. But I think it's a very interesting topic to think about right now, and then try to come up with a concrete calculation towards this direction. So it's boson jet quenching. So I mean the electrolytic bosons are color singlets, and has a very large invariant mass. So that's make it a very specific laboratory for study color coherence and decoherence. So I'll quickly say the language and then sort of go through very quickly what I mean by color coherence and decoherence. And then I'll jump to how we could use this boosted system to probe color decoherence. The idea is actually very simple, and as I'm going to show you, but there are some phenomenology that's quite interesting for us to look at, okay? And in the end, I will give you a rough estimate of in the future high luminosity LC if there's a scenario where we can study this channel, okay? Hopefully, yeah. So for color, I think I think most of the people here know in vacuum to a certain order is a very good approximation that sequential radiation is angular ordered due to color coherence, and sort of a rough argument for that, it would be that if you look at the formation time for the emitted gluons, which is just the boosted proper time. Then if that formation time that matches the sort of the angular separation of the dipole, then you could argue that, okay, for a wide angle radiation, then the gluon just cannot resolve the color dipole, okay? So that is what a color coherence means, that there's certain sort of restriction by QCD itself that the radiation has to, sequential radiation has to obey. And so if you can think of it as a sort of a more easier situation where if you have a colorless color singlet dipole, you can always go to the dipole rest frame, and then in that frame it's very simple that the color dipole just go back to back, right? And then there's a boost between what you are seeing in laboratory that you're considering the angular restriction for any angle between the dipole, but now in the rest frame, as you can see that the QCD is invariant. So you see that the out of cone or the restricted region for color angular ordering just boils down to talking about whether there's a back to a boosted direction region if there's a depletion of the radiation. Okay, so a color coherence in this case, since it's an isolated system, is quite expected that it should be there. So in QCD jets, of course, for color systems to leading color approximation, then you could decompose the color structure into a few dipoles. But this doesn't really say that we could always have the color singlet dipole physics everywhere in LC physics. And instead, the key point is that if the system is not color singlet, then there's no frame in which this color singlet nature can be exposed cleanly, because it's always color connected to everywhere in the events. Okay, so that's why like the boosted the color singlet system by itself is so useful and interesting. And in heavy ion collisions, like we are expecting that this color coherence picture will change, because not only the radiation from this color dipole itself has to resolve or not resolve the color dipole structure, but as soon as you get into a medium, then they could induce some scales for it to resolve this color dipole. That's basically the idea, right? I mean, in vacuum, there's not extra scale that can help you resolve the radiation, but in the medium, there is. And so in this week, we're sort of like always coming back to saying that, okay, it depends on the model calculations, like the median effect can be kind of like qualitatively different. But here, I just give you one specific example of about what this resolution angle is. Okay, so in terms of this Q hat, which I'm very surprised, like maybe I missed some talks, but this is called jet quenching parameter. I think everybody probably have heard of it. And then if it's not introduced in previous talk, then I'm just set the stage here. So like, and then this L is about, say, you can estimate as like the size of the QGB medium. And just to sort of like correspond to the later sort of like a theory model calculation, and here I just schematically put some rough estimate for these parameters. So Q has a 1 GeV square over Fermi. And then the physical meaning of this Q has like due to medium interaction, there's some momentum exchange between the jet or the parton with the medium. So you can think of it as a sort of like a dimensional analysis kind of estimate of how large the interaction is. Okay, so let's just say it's about 1 GeV up to the units, the nuclear units. And then the size of the medium, let me just put like a 2 Fermi-ish. I mean, it depends on whether it's a lead ion or smaller ion, but for here, like let me put it like an average 2 Fermi. And then it's just to give you an idea that what this angular, like a resolving angle is. And it's not too big, I mean, it's kind of small, but based on this model, okay? So you can imagine that, okay, the median actually is a kind of like a high resolution thing to resolve your radiation, so that your QCD jets passing through the median, you'll be seeing very kind of microscopically, and then it will do something on your QCD radiation. That is the rough picture I would like to give you here. And because of that, all the previous properties like color coherence and angular ordering may be destroyed. So I think one of the major goals we should have for and then to hunt for this qualitative feature in heavy ion collisions is to look for this type of things in data. And I'm trying to approach it from the point of view like using boosted object. And then by now it should be pretty clear to you, like, okay, color coherence and then dipole. Then how about let's just get a color dipole and then do it, right? I mean, like it's kind of obvious. And the problem is that the color singlet dipole that we have in standard model are very heavy mostly. And I want to sort of like at the moment say something, the caveat that there has been extensive studies of the dipole picture in DIS, like the photon fluctuating a QQ bar pair. But I want to emphasize that in principle, this the virtuality of this photon is dynamical, so that is not a fixed number, okay? But here the unique feature of this boson jet is that it basically has a very like a fixed mass scale, the mass of the Z or mass of W, even though it's very high, like 80 or 90 GeV, but it's a fixed scale. Then and in high energy physics, like due to like motivations like searching for the physics beyond the standard model, like the study of this boosted objects has been a very important topic in that context. But here you can see that just from the boost property that the opening angle of this boson decaying to two jets, this angle will scale just like the ratio between these two mass energy scales. So it's like m over pt. Okay, so now this becomes quite interesting. Actually, you can dial up and down the angle between these two jets or subjets if you think of it as a very big jet to start with. Then this will be a very like a perfect probe of any angular scale you want to have.
You can have the set being on shape of shell. So the mass of the set is because you are imposing a cut on the shell.
I mean, like, say, to our purpose, like, if you go to like a 100 TeV collider, maybe your boson will be far off shell, but to our purpose at the LHC, for example, then this Z is basically on shell. So like, this sits at roughly the like a fixed mass scale. Is that a question you are having, or?
So you are producing this set in the hard scattering.
In the hard scattering, say associated production Z recoiling against the some jets that people want to use the Z as a reference, and then to study the jets, you can turn that around and then study the hadronic Z decay, and then here's that is the main topic of this talk. So far so good? Okay.
So, but then so experimentally, you can look at jets, and then you look into the substructure of the jet, and you infer that, oh, did this jet came from a Z or not, right?
Yeah.
And the way how you infer it is by telling that what's the hardest substructure of my jet in the order of the mass of the Z boson.
Yeah.
This is what you will do. But you can do this even without the Z boson, right? You can just take a jet, you can look at the substructure, and you can ask, I mean, it would be a background for your Z boson.
Yeah. Sure.
Right?
Yeah, yes.
So do you need the Z boson?
I will show you. It will be useful.
Okay.
I mean, for example, like the one argument I had previously is that it's comparatively cleaner because if you have a QCD jet, it's always color connected to something else. Even though for any jet, if you measure the mass, it sets a dynamical mass scale, but it's dynamical, it can change. But here it's just a fixed value. I mean, like and then you probably want to sort of like, of course, like you can study the resolution angle within jet. That's what a lot of the work has been done. But I would say that for this, they will be more direct. I mean, like you're just using a very concrete fixed angle to probe that resolution angle. Okay. Yeah.
When you do the radian at the LHC, you measure, imagine that you don't do Q-River, you do dileptons.
Okay, good. Okay, dilepton, good.
The mass spectrum of the dilepton is not just on the mass of the cell. You get a spectrum, of course, fixed at the mass of the cell, but you can be...
Exactly, yes.
Also, we agree?
Yeah, I agree.
Something that is not.
Yeah. So I will talk about the width of the resonance. So here at the moment, but the width is not like infinite. I mean, like it's kind of narrow. 2 GeV. Yeah, 2 GeV. Yeah. And then the mass is 90. So it's like a...
Yeah, but there are LHC analysis of the Trajan being very off-shell.
Oh, Julian, no. So like I don't study Julian. I want like a real production of Z boson, and I want to boost it. And that's why I say we probably won't be able to do it until 10 years later. Julian will do it all the time, right? You can do it now also. Okay. Okay, so again, another rough estimate. I mean, as I said, like just a power counting, whatever. So like the angle between the two is the ratio. So I just give you some concrete number. So if the mass of the Z is 91, PT is this value, then pretty high PT will give you kind of small angle. Okay. You have a question there?
Can you maybe explain again why? I mean, the question is about red box. I mean, this comparison is very, very naive. It only works in very special setting. We all like see
No. So they are independent. Okay. The left-hand side is something you can dial up and down by looking at high PT, low PT jet, Z boson jet. The right-hand side is the intrinsic property of your medium interaction. And now I can study my Z boson just to try to see if I can probe the theta C.
Yeah, and I was trying to understand, I mean, there are many other proposals to do this, and they also sort of talk about the C is not well defined angle in such solutions. I just want to understand like, why, in what they're proposing, why isn't this effective? Maybe you can discuss it. What's the advantage of what a proposal where just a target is the point that is?
Oh, may not be better, but I will show you how a toy calculation, how the feature of this phenomenology look like, and then you can decide whether it is interesting or not. Yeah, you will see some, I would say, more feature plot, like a, So I think it's quite interesting. Okay, so let me move on. So I mean, like, idea is extremely simple. I mean, like, so it's just like you have a ruler or an angular scale that you can play around with, and then you try to use that to probe the median scale. And as John said, people have been doing it all the time. I mean, using various systems. So then here's just another proposal. Okay, let me just show you what is the state of the art for high energy physics. So like we need to tag, of course, we don't know, given a jet, even with two-prong structure, we don't know if it is a singly boson or not. I mean, but here's the state of the art. This is the plot I steal from CMS that is for the Higgs physics, but near the Higgs resonance peak, and then people are being already establishing that the resonance for the electroweak boson is just there after a lot of B-tagging business and then suppressing the background, and then this peak is definitely there, can be reconstructed. Okay, so like the resonance can be utilized in this case. And this is the QCD background, and on top of it, it depends on the decay channel of this Z. The dominant channel is Z to BB bar. That's why B-tagging will be useful. But you can see that it sits at the resonance peak, and then there are just three characteristics of this resonance. Of course, there's a height. You have to shoot out from the background, right? I mean, like it's a signal over background ratio. And then this height I will convert to the cross-section of this Z boson, for sure. I mean, like it's literally just the production cross-section. And other than that, there will be some position of this peak. It sits at the resonance, so it's 91 GeV for Z, 80-ish for W boson. And then this also sets another probe for you to study. And also the width of this distribution. So there are three things you can talk about this resonance. Once you are able to reconstruct this electroweak boson in heavy ion collision, which is totally non-trivial. I don't know if it has been done, but once you can do it, then you have three things to look at the same time.
So this is mostly D-jets, right?
Here there can be Z to QQ, Z to BB, and
BB is dominant, right?
yeah, BB is dominant. Yeah, the dark blue.
Can you produce on your program?
You mean influence?
Yeah, on the jet. I mean, the jet structure depends on the contrast, right?
Of course, yeah. So maybe even more interesting, so you could study the B jet quenching or something. Yeah. So there, of course, is a dependence on this. Is that a question you have? Yeah.
You don't tag the B here. Exactly. That one will be much higher.
Yes. So a lot of things is subjected to how well we could do this reconstruction. But I rely on our experimental colleagues, and then actually I talked to my friends Phil Harris at MIT, and at least him, he is quite confident that we could do it at heavy ion, even though you know him. Like he's very confident always. So. But I don't see any practical obstacle for us to study it, except that we don't have the statistics. You have a question?
So, but in this plot, these are not just simply jets which came from a Z boson.
No.
These are jets which contain two heavy B meson.
Yeah. So there's a large background, right? I mean, it sits on, yeah.
For the arguments you had in the previous slides,
yeah.
You don't need these B quarks anywhere, right?
No, but if you knew that it's a B quark, then maybe you can you can study it more.
I'm just saying that, in principle, do you just show this plot because of an example, or is it?
I just showed this plot.
Remove the DDD pass that is up on the top.
Oh, so I mean,
if you would remove this trigger, then you would have, like 1 million times more of this
yeah, let me just, okay. So all these color things are like theoretical. I mean, we don't know. I mean, like the data is this dot. There's a bump above this whatever background, okay? So in experiment, that is the only thing we see. Whether or not you will be able to reconstruct all these channels, it depends on your calculation, etc. But once you see this, the point I want to make here is that once you see this resonance, then there are 3 things you can look at. Just like if you measure jets and then look at the suppression of the cross-section here, you could look at the height, whether it's being modified. You can look at the position of the resonance, whether it's being modified, and it will. And then you can look at the width of this resonance, and maybe it will be modified in principle. So I just want to point out that this opens up a phenomenological opportunity for this boosted study. Okay, so just want to make sure this is just the idea. And in terms of calculation, so I mean, Yassin has already talked about it, and then this is his paper. So Paul and I actually sort of went on using this theoretical framework and tried to crank out some calculation and study whether this proposal is feasible in that context. And I won't go through it. It basically is resembling what Yassin had said before, and it highly depends on in this case, in this paper, depends on the energy loss probability, and then you can automatically relate that to some differential distribution, either interference or non-coherent contribution. And here I just show a few of the formula that gets into the calculation of the plots I'm going to show you later. And but I want to emphasize that this again right now is highly model dependent because you Q hat and then you have BDMPS formalism. But I want to emphasize that the previous sort of setup of why we want to do it, I think that is very generic. So Krishna has a different model calculation for the same type of system, then I encourage you to also think about what will be the phenomenology consequence in that context. So I just glimpsed through this because this is not mostly what I work on. If you have questions, you can ask Yassin and Paul. And then I just want to show you that it's work in progress, but at least one thing that we could try to get an access of the accessibility of this channel is to look at the heavy ion 101 jet quenching. So here we look at the Z jet quenching. If you translate to the height, the resonance, you'll be whether the height of the resonance gets modified. Okay, so you could measure it. I mean, you could just measure the resonance in PP, measure the resonance in AA, look at how high that resonance changes. Then you could maybe if RA is equal to 0.5, then you will see that okay, the height of the resonance gets lower by half, something like that. Okay, that's what you may expect. And here I just show you a few of the representative calculation. So since the boson is color singlet, okay, so if it is totally coherent, then this colorless thing just pass through the medium without interacting with the medium, right? So RA should be 1. This is the non-realistic but trivial limit where there's no jet quenching. That is good. Even though this boson decay hadronically become QCD system, but if it's color coherence, it just doesn't really see the color and then doesn't really see the resolving the color of the subject. It just pass through the medium immediately. Another way to think about it is to go to a high energy limit that, the two subjects just get very close to each other, and then maybe a trillion TeV collider. UZ boson just doesn't decay until it hits the detector. Then, of course, this just like a photon pass through the QGP medium, then this boson will just easily pass through the medium. Okay, so I won't say too much about this trivial limit. On the other hand, within this framework, we were able to sort of like do a hypothetical calculation for, say, if the medium could resolve these two subjects always. Now the color singlet boson decay into two quark jets, and then these two quark jets, for some reason in this limit, can be seen by the medium all the time. Then this will become two color charges, and then the jets will be losing energy according to each one of the subjects. Okay, so you imagine that this sets another upper bound that the upper bound of the energy loss and then the lower bound of the RAA that may happen. And because the nice thing about this system is that you can actually look at different PT regions and then look at how large or small the coherence or decoherence effect is. So as soon as you hit the PT hits the theta c, the resolution scale that corresponds to the median resolution, the interaction, then one should see a very clear transition from going from fully coherent to decoherent.
This is the PT of the reconstructed
jet. Boson jet, yeah. Huh? Yeah, so, yeah, yes.
So, which is itself changed.
Yeah. Again, just like a jet RAA is a jet PT, which is itself changed. Huh? Yeah. So energy loss, it has been taken into account, just energy loss. But now put the boson jets. Sorry, I probably assumed too much about the phenomenology of heavy ion. So usually what one does is that you look at hard probes in PP collisions and hard probe in AA collisions. In terms of the spectrum, what one usually do is to take the ratio between the PP and AA cross section, and then that nuclear modification factor is called RAA. And this is exactly the same thing, RAA, but for boosted boson jet. Felix, you have a question?
That's one way all the curves go to zero.
Go to Oh, good question. So maybe it's.
This is only the RAA inside what you define as the Z of the W width, right? So if each jet loses 5 GeV, it still comes out, but it's not within the peak region.
What was the selection of the jets? How you define what you consider as a jet?
Yeah, so there's no selection here. It's based on like a calculation. So I think it's so similar to since the framework, like all the induced radiation is considered lost energy. So there's no jet count, reconstruction, etc. And here we don't do jet reconstruction either in this calculation, so it's non-realistic. So you should just take this calculation with a grain of salt. This I actually have to look back and see why it goes to zero. But
this is a toy model. The genetic feature should be this. The genetic feature is that energy loss from jet crunching is none. So QT is large, we expect it to be 1, and lower QT jets should be crushed more. Right? So the energy loss should be spent on atomic behavior, right? Now the question is why it goes to zero exactly. This is a feature of the model. It's just telling you that it captures this feature that when QT goes to zero, crunching is maximum. Now you can question whether you can measure jets at zero, right? So that shouldn't really trust anything.
Yeah, maybe you should just ignore very low PT.
Because if each jet loses 7 GeV, right, which is what happens, it doesn't go away, it loses just a few GeV. But then when you experimentally look for the digest in the mass region of the W boson or the Z boson, they go up. They're in the much the jets are suppressed, but how much the dijets in the mass region of the Z boson are suppressed.
You're right. So like the mass,
Can go to zero.
sure. And then the mass resonance can change the position. But experimentally, one can correlate this mass scale, sort of like this mass window selection, by first doing a two-prong tagging and then see if you could left over with any positions for the mass resonance. So ideally, I hope we will see that, and I think we will see that. It won't be totally gone, but it will be shifted, the mass resonance in heavy ion.
Right, but then it would be covered by background.
No, it wouldn't be, because it just stands out. Sure, there's a lot of background, but it's still.
That plus on top of all the heavy ion background.
Yeah, but like you can here, you could also have a pilot, and
You're going to measure a shifting
I know,
in the setting.
I know it's challenging, but no, but I don't think it's impossible. I mean, like
Well, first you're not telling me what is the fraction of the cross section that sits on that given P.
you could talk to Yanjie. I mean, like one. Yeah, I mean, I'm not experimentalist, but Yanjie did isolation of bosons in heavy ion, and it works. So, I mean, like we have to discuss how to reconstruct this resonance, but in this talk, I wouldn't be able to address that.
Yeah. So in EV, there's also pilot.
Exactly. I mean. Yeah, I mean, like pilot may be easier because you can always look at the vertices. But I mean, it's challenging. I'm not saying that it's trivial, but I don't think it's impossible.
But maybe it helps that so Z bosons being reconstructed in heavy ion collisions, for example by Atlas. But there, the way how they did it was they looked at Z bosons with decay to leptons or something.
Yeah.
So then now, like to do this with jets, probably it's a bit more difficult, but statistically it's possible because there's enough statistics. It's just experimental.
I mean, yeah, you could do B tagging.
There's enough statistical 500 dB of the jet. They're measuring boosted.
Yeah.
That is something.
That is another thing that I will address in the end of my talk. Okay. I mean, it's not. I said we won't be able to do it until 10 years later. So you are right. I mean, like you can keep complaining, but maybe 10 years later you will be feeling that maybe it's possible.
They're presenting a phenomenological proposal of an idea that you also have
Yeah.
discussed.
I will show you some concrete. Yeah, I will show you.
Can I ask something to Wei?
Yeah.
Have the Z bosons ever been reconstructed in the hadronic channel, in the jet channel?
In heavy ion? Okay, so can I move on? Just hang on with me. I mean, like, I know it's very challenging, and then actually, we started this project 4 years ago when we were like, but I sort of got intimidated by the almost impossible scenario for this channel until I was invited to give a talk, and I said, this project intrinsically is interesting. And then I spent a few hours working with Cloudy, and then realized that, it's not impossible. So I'm going to show you my result. Okay. I just need to dig into some realistic numbers and see whether here it is. Okay. So then, at least I think I've conveyed the message that if we were able to do this, it would be great. Okay. And then now I'm going to show you in this slides very rough estimates. Yeah, it looks like not impossible. Okay. So if you assume that for high PT hard probes in PP could be done, then there's a way to crank up the heavy ion scenario so that we could do, in principle, all sorts of hard probes, just like in PP. I'm going to sort of show you a few numbers here. So like it is 2026 now, and so roughly like we have 300 inverse femtobarn of statistics accumulated in PP. Let me just where you can count. Now it is your expertise. If there's any number that just look terribly round, just let me know, okay? So here I just want to estimate that, okay, it's about 300 inverse femtobarn for PP, and then it's about 5 inverse nanobarn for, say, AA, okay? So if you just look at this, then like at raw value, then you see there's a 60,000 times difference in terms of this integrated luminosity. Okay, it's like, oh, 60,000 times difference. It's just like throw this away. I mean, how can we do it unless we just look at high cross-section events in AA, okay? But now there's some like a very cute thing that can happen. For example, of course, we all know that AA there's an advantage because there are a lot of nuclei in it, so there's some help coming from the number of binary collisions. There's roughly like a 400, say for example, the minimum bias collisions in heavy ion, say for lead collisions. Then you see that this is not just like a 60,000. It's actually not too bad. It's just like more than 100 times difference in terms of this luminosity you need. Okay, but 100 times is still kind of hopeless because we all live less than 100 years, and every year we may have 1 month heavy ion around. So you need many years to accumulate this 100 times statistics, so it's not feasible. And however, if you follow the future LC planning, and there's a proposal of trying to go to lighter ion, like colliding argon, like a smaller ion. Of course, with the advantage of a higher luminosity. And if you do the scaling correctly, that actually going to argon-argon collisions, it can help you with about a factor of 10 increase in terms of the half probe cross-section. Wait, is it something you have a similar feeling? Or some factors? There's a increase in terms of helping with the half probe program by going to lighter ion, and then that is one of the reasons why we want to do a lighter ion runs.
Increase nuclear velocity that goes to lighter ion.
Yeah.
On the other hand, of course, the nuclear energy factor will also be reduced.
Yeah, it will be reduced. And the recent studies of carbon runs, and we knew that smaller ion is actually a smaller large system. So I think that it's okay. I mean, it is not a small system. It's still a pretty significant a large system for us to study. So maybe the effect will be smaller, but I think it's doable.
The effect you are looking for is reduced.
Yeah, maybe RA become from 0.5 to 0.7 or something. Yeah, something like that. But it's not going to be qualitatively different from a large system to a small system. Okay, so again, what Wei says is really important, but I still rely on the hope that the half probe program is still feasible. Okay.
What would be the optimal choice of the
light ion?
Balance the effect you are looking for.
Do we have this freedom to choose? I mean, I thought argon is basically the only thing people talk about.
Not any in the pure field, but there are few.
Okay, but we could. There's one. So let me just put it this way: different species can help getting more access to half probes. Okay, then there's another factor of 10 missing. I mean, if we remember, we need a factor of 100 in order to match PP half probe scope program and AA half probe program. Therefore, I mean, some of you may have been talking to me, and I have been always saying that depending on the shift of the priority in future LHC plan, if there's a scenario for us to sort of extend the heavy ion round by a factor of 10, which is possible in principle. Right now we have 1 month. 10 times is a year. If this is 100, then no way. I mean, even if you have heavy ion around for 4 years, you still need to wait 10 years, and then I will have retired. So I don't care. But now it's just a factor of 10, and now you can just, I mean, without hardware upgrades, you just need to convince the physics case, make a physics case there. Then if LC is willing to do it, then it will open up a phenomenology opportunity that one cannot do before. And you have
by whole year, you mean a whole heavy ion month, or you mean a whole 9 months? Really
from January 1st to December 31st. Yeah.
Your political skills make you strong.
I mean, how can I do?
So I don't question the feasibility of being able to do this. What I just question the calculation.
Okay, sure.
Because I think so when you report the luminosity, that's luminosity which is connected to some kind of trigger you have.
Yeah.
For example, let's say you collect 5 inverse nanobar luminosity of jets above 50 GeV. Let's say that's your luminosity.
Yeah.
So the luminosity is connected with some trigger.
Okay.
And then the question is that if you have a 5 luminosity of jets which is given trigger, so let's say jets above 50 GeV, then it's not the same as having 5 luminosity of jets which were originating from a W.
Sure. So here there's nothing to do with the hard probes.
Yeah.
It is the total integrated luminosity.
So there's a trigger on it.
No. That's delivered luminosity, and then you take into account cross section.
You could take into
then you take into account reconstruction efficiency.
Yeah.
So to me, what is not fully clear is that how much the cross sections will change when you have a quenching. So then maybe because of the quenching, you're gonna kill a bunch of this W boson.
Maybe half. I mean, that's our experience. I mean, you don't immediately lose all the jets. It's about half.
Maybe close here, because the QCD jet is pressed probably more than this. In fact, this will conspire probably to enhance the signal.
Yes.
QCD jet will be suppressed more than the high.
Yeah, that's also true.
Yeah. Yeah. And you have a question? Oh, so then in terms of the actual cross-section for the hard probes, then it depends on which one you're looking into. So say the dominant production channel for boosted Z might be, I don't know, Q-gluon to Z Q. Then the cross-section can be very low. As I said, I rely on the assumption that hard probes and PP works. So they could do it, then there's no reason. If you could crank up the cross-section for AA, then there's no reason, or it should be possible. If we work hard suppressing the background, then we could do it. Okay, so with this 2 factor of 10, I think we'll be able to bridge the gap. And then we'll be open up whatever hard probes that people have been doing in PP, that us, heavy ion physicists, should be able to do it. And this is important because, as you all know, LC will be the only heavy ion machine in the foreseeable future because RIG has been shut down. And of course, the boson will never be done at RIG. So that is not directly related to what I want to talk about. But in terms of the sociology, I mean, people need to decide what they are going to do after RIG. I mean, so the LC will be the only heavy ion facility. And it's even worse. I mean, the round 3 is ending. So there's going to be a few years gap from now until 2030 before we have any heavy ion run. Okay? And starting from then, I think the priority would still be PP collisions. So there's no way that we could make this argument and then convince high energy community to have a whole year heavy ion run until I would say maybe the end of round 4. Okay? I mean, in a few years after high luminosity LC, we should be having a pretty clear picture what we should expect in terms of how much of a statistic for BSM searches, okay? So I'm sort of like the optimal time for us to talk about this like a argon run for the whole year. Yeah, hopefully, would be 10 years from now. Or after another long shutdown, maybe sometime in round 5. I hope. I mean, and then bear in mind that there's not going to be any heavy ion rounds, and then when you're lucky, you work on LC, so then you could continue work on that. But for other heavy ion physicists, experimentalists, then they're just like having to, if they still want to do heavy ion physics, they need to look at LC data. And I think it's time for our community to sort of like introduce new phenomenology also towards LC physics. And of course, there's another sort of like significant efforts like a nuclear community will make in terms of like studying the initial stages of heavy ion collisions through EIC, if you want to relate that to heavy ion. Of course, there's a whole lot program out there for many other purposes. Okay. So this is the end of my talk, and then I hope that I've entertained you before lunch.
I really don't want to sound unpolite, but you are aware of the paper about boosted force?
Sure, yeah.
Okay, because it's the same physics.
Yeah.
So, yeah.
Yes.
Be kind, at least mention it.
Oh, yeah.
I mean, this is all done there. So,
yeah.
All the scales, all the possibilities.
Yeah.
You need a whole year of heavy ion running?
Sorry?
To do what you wrote in the boosted top paper, you need a whole year of heavy ion running?
You probably for the LHC, yes.
Yeah, so that's why you said SEC.
Yeah. But there's realistic estimates of
And the problem with SEC HH is it's not only after I retire, it's after you retire, it's after everyone.
Yeah, exactly.
Always.
Oh, yeah, I want to comment on the top. Okay, I want to comment on the top paper. Yeah, of course I am aware of it, but it just seems like unnecessary to go to the top if we were able to W singlet by itself. So I mean, like, of course I need to. Yeah, of course I need to refer to it. Yeah.
There's another factor. If you want beta X, you need to put the efficiency of beta X.
Yeah.
That brings your efficiency down.
Yeah. So I just don't want to be impolite with that. Yeah. I knew that paper for sure. Yeah. And there's no reason why I didn't know that paper. I want to suppress that.
So I guess one question to investigate is whether you will. Well, I guess first thing you want to foresee is you will see the peak in the when you look at the map.
Yeah.
And whether you will gain by tagging the D or not. Of course, the physics will change, but as the first step, you want to be able to see the CP. I would imagine that the plot you showed, without tagging the D, you will not be able to see the peak composition, but then you will be completely overwhelmed by the.
So I mean, that's not my impression actually, and actually for that plot, it's not just the BB bar channel that is shown there. I mean, it includes all sorts of channels. Yeah. 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 And then I think at the moment, I think at least for CMS, I don't know whether they specific have taggers and implemented, but now they all use like a transformer. So I'm not very sure what is the state of the art reconstruction of this resonance. But my impression is that the reconstruction of this has been established a few years ago. It could only be better.
Oh, no, I'm just saying that
we need B tagging.
Yeah. Without that, I would imagine the 2CD backward will
Yeah, I agree with that.
Maybe
Oh yeah, I would do that too. Yeah.
And that's why you see, you can also see the P from the location of P and the shape of P already tell you the
Exactly. Yeah, I didn't mention the other quantities. I think quenching, like a suppression of the cross-section by itself, maybe just very conventional observation you will have for usual jet quenching. I think the interesting sort of like facility here is that you could look at three things at the same time. So each one of them would be modified with a different sort of phase space problem in terms of physics. The mass shift and then the suppression of the cross-section will not be 100% dependent. So like I think this makes this a very sort of interesting channel for me, at least.